Hey, Calc students, time for another FRQ. Free response question from AP Calc AB exam from the year 2017, and the question is number 4. So this is a non-calculator question, and it's one of those questions that's a little bit of a blend of a rate combined with a differential equation, a little bit of a curious question. And let's go ahead and read and see if we can get understand the nature of the question. So here's how it begins. It says at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time equals 0, or right when they took it out of the pot, and the internal temperature of the potato is greater than 27 degrees for all times t greater than 0. Or in other words, it never cools off to be less than 27 degrees Celsius. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies the differential equation dH dt is equal to negative 1/4 times the quantity h minus 27, where h of t is measured in degrees Celsius and h of 0 is equal to 91. Well, just to start, there's several little bits and pieces here regarding just vocab that they're seeing if you know. Let's see if we can just draw a silly little picture here and see if we can understand what's going on. So there's our potato. So we take it out of the, or off the stove, and when we do that, it's 91 degrees Celsius. Okay? And as you take it off, it cools, so it would make sense that it's cooling off the entire time you take it off the stove, but it never does get cooler than 27 degrees. Sounds reasonable. And then it says that the differential equation that satisfies the temperature of the potato is given by dH dt is equal to negative 1/4 h minus 27. And then they tell us that h of t is measured in degrees Celsius. So whatever that function is, it's in degrees. Okay? So a couple things here, just that they're kind of quizzing you on just your lingo and your vocab. Do you understand? So something that I discuss quite a bit is that whenever you see something that looks like this, dH dt, there's several answers to what is that. And one of the most common answers you would get, or what you saw most early in the year, is that this is just the third notation that we would use for a derivative. And that's true. And then you would say, well, I think then if it's a derivative, then it's a slope of a tangent. That's true. And then the third most common thing to say would be, oh, well, that's a differential equation. And that's also true. And so depending on the context of the question, you can answer all three of those correctly. But then there's kind of a fourth thing. If you say, well, if it's a derivative, that's true, but what do derivatives represent? And I'm going to parentheses put this. I'm going to say it represents instantaneous rate of change. So let's see what they're giving us. They're giving us a differential equation, and what this is a rate of change. It's a derivative. It's the rate of change of the temperature of the potato. So h of t, which they didn't give us, h of t is the function that tells you the temperature of the potato. That's why it's measured in degrees. So whatever h of t is, it's going to give us the temperature of the potato at any given time. So dH dt is equal to the rate the temperature is changing. So if you integrate the rate the temperature is changing, you'll get the temperature, how much the temperature changed in an interval. So when you see this over here, you want to be thinking, oh, well, this is just h prime of t, which is also true. It's the derivative of this function. It's written as dH dt. So that's why when you see this, you'd think, well, I think it's a differential equation type of function. I'm probably going to wind up solving the differential. That's true eventually, but they're also going to ask you a few other questions here as we go. Now, one thing that's also really important to notice on this question, it's very easy to get tripped up by this that you want to notice at the beginning, is that the variable t is equal to time, and the variable h is equal to temperature. So it's very easy when you're doing these kinds of questions to assume that t stands for temperature, and you can confuse yourself midway through the problem. So t is always going to be time. These are rates of time, rates with respect to time, and h is going to be the temperature. So don't let that trip you up. So I'm just going to leave this sitting here as we attack this. We only have 3 parts here, and let's see what we can do. So part A says, write an equation for the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato at 3 minutes. Well, you've done this quite a few times in calculus, and you say to yourself, well, they want the equation of the tangent. That seems to be a big topic. And so you could say, well, I'm going to do slope-intercept, or you could say you're going to do point-slope. So this would be your first thoughts. Whichever one you want to use, doesn't matter. So I need to write the equation of the line tangent at t equals 0. Well, I need a coordinate. Well, they tell me at time is 0, and they said earlier in the question, here it actually says h of 0 is 91. So this is handy. We have a coordinate, 0, 91 degrees, and now all we need is our slope. So we have x and y, we need our slope, or here we have x and y, we need our slope. And that's where you say, oh, well, back over to here, dh dt is the slope of the tangent, so I just need to evaluate that here. So I'm going to say, actually do my work over here. I'm going to say my slope of my tangent at, and this is that's just a vertical line. They use that notation sometimes. At 0.91 is equal to dh dt. They use a capital H, evaluated at 0.91, and then we'll just put that into the equation, or the tangent, which is right up here. So this was given. So it's going to be negative 1/4. I need the h value, which is just 91 minus 27. So 91 minus 27, I think that's going to give you 64. And then we have a fourth of 64. We wind up getting negative 16. Okay, so now we can come over here and we can say, well, I have a coordinate 0.91. My slope is equal to negative 16. And hopefully what you notice that since your x value is 0, this is actually your y-intercept as well. So actually slope-intercept might be a little easier way to go because we already have our y-intercept right here. So we could just say, oh, well, I guess it's going to be y is equal to my slope, negative 16. And make sure you put in t, not x. And then plus 91. So that would be the equation of the tangent. And now they say to use t equals 3 to approximate it. So then we could say, well, at t is equal to 3, I'm going to say y is equal to negative 16 times 3 plus 91. So this is going to be negative 48 plus 91, and that's going to give you 43 degrees Celsius. So those are our 2 answers right there. So there was our tangent approximation, and here was our actual evaluation at t equals 3, 43 degrees Celsius. So that would make sense. It was 91 degrees, took it out of the pot, and it cooled off pretty quickly. After only 3 minutes, it's down to 43, but that makes sense. So the temperature's going down the whole time. Okay, now part B, kind of interesting. It says use the second derivative, so that's just the notation for the second derivative, to determine whether the answer is an underestimate or overestimate of the internal temperature of the potato at time t equals 3. So if you're confused about what they're looking for here, I'm going to give you 2 potential graphs that they're looking at. If we were to graph this, here's the 2 things that could have happened. You could be looking at a graph that the function looks like this, and here's the equation of our tangent. Okay, and this is at the point, we used approximate at 3, but we would say this point here was 0. Okay, so actually, this is not the actual one we're doing here, but at x is equal to 0, that's our point of tangency. We would say, well, we're going to use this to approximate 3. Well, what you could see here is if this is my tangent, and this is the actual graph up here, if I'm using the tangent to approximate the temperature at 3, you can see that the tangent is below the actual function, so it's an underestimate. And the reason is because the function's concave up. But maybe it looked like this. Maybe the function was doing the following, and so I'll draw this a little bit closer here to the x-axis. Maybe this is what's going on. And there's your tangent. And so this was 0, and we're at 3. And you could see if you're concave down, it's going to be an underestimate. And so that's what they're wanting you to figure out. This is the hint they're this is what they're wanting you to determine, is what's going on at the point of tangency. Was the function concave up or was it concave down? If it's concave up, your tangent's below, it's an underestimate. If it's concave down, your tangent is above, and you have an overestimate. So just figure that out. And the way you figure out concavity is by the second derivative. So they gave you a big hint here. They said use d squared h over dt squared, notation for second derivative. Well, you have to be careful here. It's an easy mistake to make on this one. So what I'm going to do first is I'm going to recopy the original derivative. So dh dt is equal to negative 1/4 h minus 27. So this is what we have to take the second derivative of. So what I'm going to do is I'm going to put a bracket around it, and I'm going to take the second derivative with respect to t, so I'm going to take d dt of that. If I do that, notation-wise here, I'm going to get d squared h over dt squared is equal to, and we just have to take the derivative of this. Now, I'm going to rewrite this. This is one of those weird things that tends to confuse a lot of students. So to avoid the confusion, I'm just going to distribute my negative 1/4, and it makes it so much easier to see here. Negative 1/4 h, and then we would get plus 27 over 4. So those are the same thing, just distributed. So let's take a look here. I'm going to take the derivative with respect to t of negative 1/4. Well, the derivative of negative 1/4 h is negative 1/4, but you got to be careful, because I'm taking the derivative with respect to t, and this is an h. So my variables didn't match, I got to represent, so I have to multiply this by dh dt. Right there is where the most common error is. Then the derivative of a constant is 0, so there's my second derivative. Well, if this is my second derivative, I have to replace dh dt with what dh dt was originally, and it's actually sitting right here. So it's negative 1/4 dh dt. So that's going to be negative 1/4, and I'm actually going to replace dh dt with what it is. Negative 1/4 h minus 27. And that's going to give me, distribute the negative here, or the negative 1/4, I get 1/16 times h minus 27. So everyone, there is my second derivative right there. Okay. Now what the question says is to use this thing to determine whether or not this is an overestimate or an underestimate. And it's easy just to miss this. Now, B is a fair amount of work here. It's only a 1-point question, so if this throws you, don't worry about it. But anyway, the point being, we got our second derivative, and we're supposed to use that to figure out concavity. Well, here's the little other hint in the question where you figure this out pretty easily. It says back in the question, it says the internal temperature of the potato is always greater than 27 degrees. So back over here, when I said the potato cools off, it never gets cooler than 27 degrees. So therefore, if you look at this thing, it's always greater than 27. Well, if this is always greater than 27, h minus 27 is always a positive number. Positive number times 1/16 means this is always going to be greater than 0. If your second derivative is always going to be a positive number, it means you're concave up. If it means you're concave up, it means your tangent was below, and it means you had an underestimate. So that's what I'm going to say. I'm going to say underestimate because d squared h over dt squared is always positive. Okay. Now, I'm sure you might be looking at this and saying, well, isn't the temperature always decreasing? If the temperature is always decreasing here, how could this be concave up and decreasing? Well, remember, you can be, if your function is increasing, you can be we're decreasing here. Our function can be decreasing and concave down. A little bit hard to see there. We can be decreasing and concave down, or we can be decreasing and concave up. And so our tangent, it had to be more in this kind of behavior here. So even though I drew this one, this was just an example of these sketches were not representing the actual differential equation, it was just the concept in general. So it looks like we must have a situation where it was 91 degrees, and it keeps decreasing, and our tangent came through here like this, and it was an underestimate. Okay. All right, let's move on to part C. So part C, that's the only third part of the question. This is where all the points are. So let's see what's going on here. So part C says, for temperatures less than 10 degrees, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation dg over dt equals negative the quantity g minus 27 to the 2/3, where g of t is measured in Celsius and g of 0 is still 91 degrees. Find an expression for g of t based on this model. What's the internal temperature at 3 degrees? Well, now they decide to say, now that you've done all of this work over here with this differential equation, we're going to give you another differential equation to solve. And so this is more of the classic differential equation type of question where you're going to get most of your points by solving a differential. Do you know how to do that? And so I'm going to get rid of this, and this is where we're going to get most of our points, and this is where all of the work has to be done. So let's copy this up here, and let's see if we have skills at solving a differential equation. So way up high here, I'm going to say, all right, we've got dg now, dt, is equal to negative, parentheses, capital G, minus 27 to the 2/3. All right? So now it's, do you know how to solve a differential? So you should know your first step is going to be to separate your variables. Now, you might not know what to do with this negative. I'm going to give you a hint here. Whenever you have this kind of setup, leave the negative on this side with t and bring this over. So actually, this is going to wind up being dg over. I'm going to divide this over. So in the denominator here, I get g minus 27 to the 2/3. And I bring over the dt, and I just have that negative sitting there. I'm going to call it a negative 1 times dt. So all I did was separate my variables. Now at this step, I need to integrate both sides. So we're going to integrate, and I'm going to go ahead and put a 1 there. And this is g minus 27 to the 2/3 dg, and that is equal to the integral of negative 1 dt. Okay? Now, on this left side here, I want you to look at that. What we're going to do is bring that up to the numerator, and we're going to make a negative exponent. I mean, it's an old skill from algebra. So I'm going to rewrite this side. I'm going to say, all right, this is going to now be, bringing this to the numerator, I'm going to get g minus 27 to the negative 2/3 dg. And this over here, I'm just going to leave this like this, negative 1 dt. So now we're dealing with something that we should be able to handle. This right side's much easier here. So we're going to integrate negative 1. We're just going to get negative t, and I'm going to put my plus c over here. Only one side's going to generate it. I always put it with the independent variable, which is time here. So remember, g is now representing temperature. Now, this little integral right here, several of you could just recognize we do this in one step. Technically, we have a little u sub here. So we don't often do this, but I'm going to put my u sub to the left here because of the nature of the question here, the way it's set up. So if I went over here and I said, well, I'm going to let u equal g minus 27, you notice pretty quickly we get du is equal to dg. Whenever that's the case, you can just do a shortcut integration here. But I'll go ahead and put the steps in case you were confused. So this technically would be u to the negative 2/3 du. I replace dg with u and the inside with u. Add 1 to your exponent, divide by your new exponent. So negative 2/3 plus 1 is 1/3. Divided by 1/3 is 3. So this winds up being 3 u to the 1/3. And we're going to leave this over here. Okay, I'm going to put u back in, which was g minus, I'm going to make this a cube root, g minus 27 is equal to negative t plus c. Okay, now you could continue to solve here, but if we go back to the question, it tells us here they want a specific solution for 0, 91. So we're going to find a specific solution, not just the general solution. So what I'm going to do here is solve for c. So at this step here, I want to solve for c. And the way I solve for c is I'm going to put in 91 and 0, and because that was given. So I'll put that over here. It was given that g of 0 is equal to 91 degrees. So what do we get here? 3 times the cube root of 91 minus 27. And since this is non-calculator, this is probably going to work out kind of nice. and we get negative 0, technically, plus c. So obviously that's going to drop out. So let's see, 91 minus 27, we're going to get the cube root of 64, which is 4. So this whole thing turns out to be 3 times 4, so we wind up getting 12 is equal to our c value. Okay. So now we're going to take that and we're going to go back to this step and put it in there. So now we get 3 times the cube root of g minus 27 is equal to negative t plus 12. Now, we're going to solve for g. That's like solving for y in this question. So we're going to divide both sides by 3, cube both sides, add over the 27, so just a little messy algebra here. All depends on how you want to do that. So I'm just going to make this cube root of g minus 27 is equal to, dividing both by 3 here, I'm going to make this negative 1/3 t plus 4. And then I'm going to cube both sides. So I get g minus 27 is equal to this whole thing cubed, and then add the 27 over. So it looks like g, or g of t, you can write it either way, is equal to negative 1/3 t plus 4 cubed, and then we add a 27 on the end. Okay, and that's our equation. And again, you can put g of t there. And in fact, in the question says find an expression for g of t, so we might as well go ahead and replace that there. So there's our expression for g of t. So we have that part. That's worth the majority of your points right here. And then we need to use this to find the internal temperature of the potato at 3. So then our final step here is let's just go ahead and figure out what g of 3 would be. And so we get negative 1/3. Negative 1/3 times 3, this is going to be negative 1. So we get negative 1 plus 4 cubed plus 27. So negative 1 plus 4 is 3. 3 cubed is 27. So we get 27 plus 27. So we get 54 degrees Celsius. Okay. And that part C, that's 5 points. That's the bulk of the question right there. So if we go back to the beginning, they asked this a lot, right? The equation of the tangent. And what were you getting tested on? Did you know that a differential equation is actually a slope value? And we had those notes written here, but they were erased as we were doing the problem. And just solving for that, that was 2 points, pretty straightforward. Use your second derivative to check concavity to see if it was an overestimate or underestimate. And this was not too bad, but unfortunately it was one of those questions that was easy to make a careless error. So you might have missed that one. But again, this was 2 points here. Oops. That was 2 points, this was 1 point, and this one being 5 points right here. This is the bulk of the question. Or sorry, this was actually 3. It was worth 3 points. And then 5 here, can you solve a differential? Which hopefully you're getting good at here. Just all your integration skills, and then solving for C, put it in and get your estimate. Okay, so there it is, AP Calc AB 2017 number 4 differential equation style. So thanks for watching. See you next time.